And welcome back as we continue our cosmic journey through our own galaxy. Let's go ahead and discuss the spiral structure that is very familiar to most images we see. So let's start by looking at the arms of the Milky Way itself. Here, of course, we can see the Milky Way as if we were to look at it from above. This image kind of shows us that the Milky Way galaxy has a modest bar in its central regions. We can see that right here. This is the bar that we're talking about. And we have two main spiral arms. We have Sectum Centaurus, which is this main arm that's spinning out here. And then we have, of course, the Perseus arm, which is spinning over here. These, of course, are coming out of the ends of the bar, and they're actually wrapping around the bulge here in the middle. Now, if you notice, we do have some more minor arms here, such as the Sagittarius and the outer arms. But you'll notice that these have fewer stars in comparison to the Sectum Centaurus or the Perseus arm. If we want to zoom in a little bit on some of these sections of our galaxy, you might be wondering, where exactly is our own sun? Well, our sun in our solar system by proximity in us is, of course, going to be right in here in the Orion Spur. Now, the Orion Spur is a relatively minor spiral arm and is located between two other arms. So, for example, you can see in this image, we have the Perseus arm and the Sagittarius arm, which is where this spur is sitting. And you can see we have some white lines, of course, representing other noteworthy objects that share this same feature of the arm that our Milky Way has for our sun. So, for example, if we look right here where our sun is, you can see very close by we have the Orion Nebula, which, of course, is something that we've talked about previously. Now, an important thing to keep in mind is the further we are traveling, and the farther we try to look from within our own arm of the Orion Spur, the more dust we have to look through within our own galaxy. And so that dust will, of course, build up and make it hard to see with visible light. So let's go ahead and talk about the formation of the spiral structure itself. Now, at the sun's distance from its center, the galaxy does not rotate like you would expect a solid wheel or a CD inside of a disk player. Instead, the way individual objects turn around the center of the galaxy is more like how we think about the solar system. Stars, as well as the clouds of gas and dust, obey Kepler's third law. This means that objects farther from the center take longer to complete an orbit around the galaxy than those that are closer to the center. Stars and interstellar matter that are in these larger orbits trail behind those in the smaller ones. This is an effect we call differential galactic rotation. Now, differential rotation would appear to kind of explain why so much of the material of the disk of the Milky Way is more concentrated into elongated features that resemble these spiral arms that we're looking at. Now, no matter what the original distribution of the matter might be, the differential rotation of the galaxy can stretch it out into spiral features. But, of course, this picture of spiral arms does present astronomers with a little bit of a problem. If differential rotation had been applied roughly over the 13 billion year history of the galaxy, it would have wound the galaxy's arms until all semblance of spiral structure disappeared. But did the Milky Way have spiral arms when it first formed 13 billion years ago? What did its shape to have? And with these spiral arms, once they formed, how do they last for a long time? So this sketch actually shows how spiral arms might form from irregular clouds of interstellar material stretched out by the differential rotation rates throughout our galaxy. The regions that are farthest from the galactic center take longer to complete their orbits and thus lag behind the inner regions. Since many galaxies have spiral arms, they must therefore be longer lived, and there must be other processes at work in order to maintain them. Now, it has become possible for us to observe the structure of very distant galaxies and see what they were like shortly after they began to form more than 13 billion years ago. What these observations show us is that galaxies in infancy had bright, clumpy, star-forming regions, but there was no regular spiral structure. Now, over the next few billion years, the galaxies began to form spirals that lost their massive clumps, and they kind of developed more of a central bulge. Now, the turbulence in these galaxies decreased over time, and so then rotation began to dominate the motions of the stars and gas, and stars began to form into a much quieter disk. Smaller star-forming clumps began to form fuzzy but not very distinct spiral arms. Then we got bright, well-defined spiral arms appearing only when the galaxies were about 3.6 billion years old. Now, initially, when we look at these galaxies, they have about 2 well-defined arms. But if we look at our own galaxy, we can see that we have some minor arms and stuff like that. And so these multi-arm structures that we see within galaxies much like our own appeared only when the universe was about 8 billion years old. These arms then became self-perpetuating and could survive for at least several billion years. The arms may change also in their brightness over time as star formation comes and goes, but these are not considered to be temporary features. The concentration of matter in the arms exerts sufficient gravitational force to keep these arms together over long periods of time. So we start talking millions to billions of years on our time scale.